Okay, lecture 45 notes, hypothesis testing for a mean, examples part 2. I think we can zip through these very quickly. These next two are also based on problems we looked at earlier, but again, I changed the numbers a little bit. When I finally worked through how I wanted the tests to go, I wanted certain things to happen to illustrate certain ideas, so they're very close to, but not identical to stuff we looked at earlier. All right, example 2. The mean diameter of a certain type of tumor 2 months after discovery is 8 millimeters. At the 0.5% significance level, and again, that might be a typo. I need to check on that before I post that for you guys. I'm going to do it at the 0.5% significance level. We are going to test the claim that a new type of therapy will reduce the size of these tumors in that 2-month period. So we'll apply the therapy to 40 individuals with these newly discovered tumors, and at the end of the 2-month period, we'll record the diameters in millimeters of the tumors. So we're getting this data set, right? We'll have a 40 data point sample. From that sample, we compute the sample mean, and we get it to be, let's say, x bar equals 6.8 millimeters, and the sample standard deviation S is 2.6 millimeters. What are the null and alternative hypotheses? Okay, so number 1, what is the null hypothesis? All right, I am hoping that the claim here is that we want to claim that this new type of therapy will reduce the size. That's what we're hoping for. So null, nothing happened. The new average size will still be 8 millimeters. What we're sort of hoping, the thing we're testing for, is the alternative hypothesis, and that will be that, hey, they shrunk, right? So it's different than what we've done before. This is now a left-tailed test. So the question will be, is the test statistic we get, calculated from the sample mean, low enough, unusually low enough for it to think, yeah, this probably isn't true, probably we need to shift the curve to the left, and really the new mean is smaller, right? Or is it not low enough, and no, we don't have a good reason for shifting the curve, we think it may still be at 8 millimeters. Okay, part 2, draw the probability curve showing the critical value, significance, and rejection region. So we're basically setting up the environment in which we're going to run the test here, the statistical part of the test. So this is t random variable, and the degrees of freedom are, well, sample size is 40. I didn't write all that down because it's there. Sample size is 40. We subtract 1 and get 39. Okay, we want I'll just say here, alpha is 0.5%, that's 0.5%, that's 0.5 over 100, which is 0.005. So it's pretty stringent, right? We are going to put a critical value, that's a small tail probability. Critical value is going to be out quite a ways, and so the test statistic will have to be pretty unusual to get beyond it, right? We're setting up a stringent requirement for us to get to where we might reject the null hypothesis. I'm almost getting a little ahead of myself. So what do I have here? I have here, if I were doing a right-tailed test, we would call it t sub 0.005, but since it's a left-tailed test and we have symmetry here, it's just the negative of that, right? So I got to go in my table somewhere and figure out what t.005 is, and if I do that for degrees of freedom 39, and the table I have had a line for degrees of freedom 39, and it had a line for area in one tail, 0.5%, and it was negative 2.708. So this is negative 2.708, 708. All right, so so here's the rejection region, right? Out here. Rejection region, I'm going to abbreviate. That's the rejection region, is all the values along that line, right? And the tail probability is 0.005 out here. Alpha 0.005 out there. All right, that's 2. 3 is compute the test statistic and place it in its appropriate place in the graph above. I have to probably get some new markers here. So I want t-score of the sample mean, and what am I going to call the random variable? Let me just call it x, so I can say that I'm looking for the t-score of x bar, okay? That's just kind of a generic name for a data value, right, or a random variable, so we'll just use x bar. Okay, so it's a t-squared of x bar, assuming that h naught is true, as always, so it's x bar minus that value of the mean divided by s over the square root of n, right? And that gives me x bar is 6.8 millimeters minus the assumption of the mean under the assumption of the random variable, under the assumption that the null hypothesis is true, and s is 2.6 millimeters, and I want to divide by the square root of 40. All right, I usually like to pick numbers where you square root easily, but I figured, well, that's not necessarily being realistic. So, you know, we can use calculators. If we do all that, we get negative 2.919. And look, that, I say put that up here in this graph. It sits over here, doesn't it? It's to the left of negative 2.708. So it's in rejection region. So I know that we're going to reject h sub 0. But I also say, what about the p-value? All right, you can't, in most tables, find the p-value for this. I already know it's going to be less than 0.005, right? I know that because it lies to the left. I don't need to find the p-value. But if you use technology, and you can go on the web and type in a p-value calculator, which is what I did, and it will actually compute the p-value. So what's it doing? It's taking this number, negative 2.919, it's putting it here, and then it finds the area under the curve to the left of that, right? The tail probability, the tail area. And it finds it using an algorithm that involves calculus. It's way beyond what we're going to do in this class, but you don't need to know it because it'll just spit the number out for you. It turns out to be 0.2902, and that's less than alpha, right? Alpha was 0.005, so that's less than alpha, so reject. But I said, because we already knew that up here that we're going to reject, but it's good to look at it that way as well. You never have to find this, right? You're not going to be asked to find it, but you should know you can find it on the web using a calculator, and it's using some kind of high-powered mathematics to come up with it, but you know, don't go digging through a table looking for it. Okay, so we reject H naught. So step 5, at the alpha equal 0.5% significance level, again, don't abbreviate, please, like I am. You know what? You B, right? Because it looks like it really worked. There is sufficient evidence. To reject, remember, what are we going to reject? We're going to reject H naught. So reject the claim, I'm just going to say that because I'm running out of ink here. Reject that the mean of tumors, diameter, doggone it. Mean, let me just say tumor diameter is 8 millimeters. Oh, using this treatment, using this therapy. Okay, I'm running out. I'm not going to write anymore, but you could add, it appears that the therapy shrinks the tumors, right? That's what seems to be happening. Okay, and I want to stress that we set for ourselves a high bar, right? A very low significance value, put that critical value out here so far that we had to get way out here in order for us to reject the null, all right? So I have a pretty strong reason to believe that it really does work, right? Okay, again, as I've said numerous times before, it could be that it didn't work, that the mean still is 8, and we just ended up with an extremely unusual value for our mean, right? The t-score is just way the heck out here, just randomly happened to be. It's just very unlikely, right? So we tend to want to reject this and believe that this is what's happening. Okay, how are we doing? We're doing all right. I'm going to do one more here. Okay, so start reading the next one. And again, it's very similar to one I talked about before, in terms of the null and alternative hypotheses at least, but I've changed the numbers somewhat just to make things come out so I can illustrate some important ideas. Okay, number 2 says, the average age at which a child first begins to read is 68 months. We'll test this claim at the 5% significance level. We observe a random sample of 50 children and record the age of each in months when he or she first begins to read. We compute the sample mean age to be x bar equals 70 months and the sample standard deviation to be s equal 8 months. Null and alternative hypotheses. All right, this is one where the statement is a statement of equality. I'm giving you straight out the null hypothesis, right? So the null hypothesis is that the population mean is 68 months. Since I'm giving you that, the alternative is not just greater or less than, it has to just be that mu is not equal to 68 months. So this is what we call a two-tailed test. All right, step 2, probability curve. That's good. Okay, probability curve. It's T, and what's the degrees of freedom? Well, if you look, it should be 50 minus 1, which is 49, right? My table that I was using doesn't have 49. So I can use this rule of thumb that says pick the closest one that's less than. I'm not going to do that. I'm just going to pick the closest one overall. So I'm going to use degree of freedom equal 50. And you can put a little parenthetical here. I just don't want to crowd it out. Should be 49, but we only have 50, and it's going to be close enough. The difference between 49 and 50 is so tiny, it's just not going to matter. So please put a little parenthetical that, you know, should have been 49, but we're working with what we got. All right, now here's the deal. It's a two-tailed test, and my significance is 5%. What that means is I have a cutoff back here and a cutoff, you know, symmetrically over here, right there. And the total significance, the total area for rejection is 5%. I want it to be symmetric here, so I want 2.5% here, 0.025, and area, and I want 0.025 area here, so this is area, right, and this is area. Okay, so see, I've split the area up into 2.5% on each side. That's what this is. 2.5% here, and 2.5% here adds up to 5%. So what I need is I need T 0.025 here, and I need negative over here. And the rejection region, let me go ahead and see if I can change color here. The rejection region then is all this and all this as well, right? I am going to say that the value I get is unusual if it lies out here or out there, right? Neither unusual, large or small, just if it lies far enough away from the mean. All right, and so what do I get for my values? I get here, I did that right, I get 2.009. Yeah, and so this will be negative 2.009. All right, and I think I have it all worked out there. So now ready for step 3, the test statistic. It will be the t-score again, and it will be x bar minus mu sub 0 over s over the square root of n. You should really get used to that, right? You're going to see that a lot. What is x bar? I look it up, and I find x bar to be 70. Minus my mean here is 68. You have to make sure, you know, pause and make sure you know where all these numbers are coming from. One of the problems students have is they start mixing and matching numbers all over the place. No, x bar is what I got from my data, and I told you there. Mu sub 0 is what the null hypothesis is saying, so I know it should be 70 minus 68. The sample standard deviation is 8 divided by the square root of 50, all right? And we do all that, and we get 0.66 roughly. We get about 0.66.
That is an error. You actually get about 1.77. Sorry, I don't know how I got 0.66, but you should work that through. This number right here, 0.66, should be 1.77. And again, you should be able to work that through and see that for yourself.
Which would lie, that's my test statistic, it would lie somewhere right there, you know, not in rejection region.
Okay, where would 1.77 lie? Here's 0.66, and so I put it way over here. 1.77 would lie farther out, but not all the way out past 2.009, right? Not all the way out past the critical value. So it would lie maybe about right here where my mouse is, my cursor, or my arrow is. So it's still in the fail to reject region. It's still not in the rejection region. So my ultimate conclusion is not altered by the fact that I got the wrong number there, 0.66. The true number is 1.77 again, but that's still, everything is going to go through just fine, all right?
Not in the rejection region. It's not unusual. And if I check the p-value, this is really good. I want to show you this. What is the p-value? Well, most p-value calculators will test, this is going to seem maybe a little odd to you, but they will tell you the p-value, if you put it right here, this is the test statistic, 0.66, all right. They will give you the p-value for a one-tailed test and for a two-tailed test. For a two-tailed test, which is what we have here, what I want is this tail probability, but I also want, if I fold it over here, I want this tail probability. I want to add them up, all right, because I'm thinking of the tail probabilities or tails probabilities associated with this 0.66 are the ones in either direction because I'm not considering whether it's bigger or smaller, just more unusual. So if I compute that, again, you have to go to a site and get it. I will get it to be like 0.512. So half, roughly, 51.2% of the area is contained in here and here. So half of it is here and half of it is there. Anyway, that's a lot bigger than alpha, right? 5%. This is 51.2%, bigger than alpha. So again, we reject H0. All right, so finally we reject, forgive me, fail to reject. I'm terrible. It's not in rejection region. So fail to reject H0. Just so we fail. And I'll write that up here a little bit better.
Okay, so let's just make sure we got this now. Of course, this number down here for the p-value is wrong because it was calculated for 0.66. Using 1.77, which is about right here again, I'm going to want the tail probability out here, and then I swing over, fold it over, and get negative 1.77 and go to the tail probability to the left. I want to get both of those, and if I use my little online calculator, I get that the two-tailed probability for 1.77, the two-tailed p-value for 1.77 is about 0.083. Okay, 0.083 or 8.3%, which is still bigger than 5%. It's nowhere near as big as 51.2%, but I don't care about that. We don't care. We only care that 8.3% is bigger than 5%. So comparing p-value with significance, we still see that we failed to reject. And again, we didn't even need to do that because we got that our test statistic was 1.77 and it lay in the failed to reject region, but we did the p-value test as well, and 8.3% is bigger than the significance, so we failed to reject. All right, I think everything else goes through fine. It's just I had those numbers mixed up, and again, sorry about that.
So we fail to reject H0. What we say is, then our final conclusion is, at the alpha equal 5% significance level, which again is not all that stringent, you don't have to go out too far to get beyond it, right? With the test statistic value. At the alpha equal 5% significance level, there is insufficient evidence and I'm going to change my marker again. I think it was this one was good. There's insufficient evidence to reject the claim. To reject the claim that the mean age at which children first begin to read is what you said, 68 months, right? We are failing to reject the null. I keep wanting to emphasize, it is the null that we are failing to reject here. So there is insufficient evidence to reject what? The claim that the mean really is 68 months, okay? We don't have good reason for believing that it is different than 68 months. Keep in mind, always the final conclusion is stated in terms of rejecting or failing to reject whatever the null hypothesis is. Let's stop here.